Hi guys, welcome to the notes for H2-7. This is day number 2. Our objective is to explore a few more parent functions and identify their characteristics and behaviors. So in the previous lesson, you looked at linear functions, you looked at quadratic functions, cubic functions, and absolute value functions. Okay, so you looked at, their graphs, their parent equations, which you'll see on this page as well. Remember, if you graph these parent equations, it gives you the parent graph. And then we looked at the values of A, H, and K and how they work with each of those functions. Today we're going to do the same thing with square root functions, rational functions, and exponential functions. And you'll see the parent equations for each of those also written on the right side here. Let's get started. So for a square root function, we're going to go ahead and graph the parent equation on this one. So y equals the square root of x. This is the most basic square root function you can have. Now, if you were to make a table of values to get points to plot this function, one thing you would notice is that when you try to plug in negative numbers, right, if we're going to try to plug in these input values in for x, the negative numbers don't work, right? We can't take the square root of negative 2, I'm sorry. We can't take the square root of negative 1. So therefore, we have to look at numbers that do work. So the first number that will work is going to be 0. If I try to take the square root of 0, I get 0, because 0 is a perfect square. If I try to take the square root of 1, that's going to be 1, which is a perfect square, right? The square root of 4 is a perfect square because it gives us 2. Square root of 9 is 3, and the square root of 16 is 4. So the points that we really want to focus on here are on this T-chart I just made. We've got 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. Let's plot those on our coordinate plane. So 0, 0, 1, 1, 4, 2, 9, 3, and then 16, 4 doesn't even fit on there, but we'll connect it, and what you'll see is this makes a shape that looks a little bit familiar, right? If we had gone the other way too, you would think, oh, this is like a parabola that's on its side, which is correct. However, we only are putting down half of it. If we had the bottom half, it wouldn't be a function anymore. So this is what our square root function looks like. Some people call it a shooting star. Some people say it looks like a radical symbol almost. Okay, but the values that you need to make sure you know are these ones on this little T-chart that we made. Right, 0, 0 would end up being like our H and K value, and we'll talk about that in a moment. But we're going to plug in those points. That's what it gives us. That doesn't mean there's no points in between, right? There is a point here at 1.5, at 2, 2.5, 3. They just don't give us nice clean answers. That's why we were focused on just using perfect squares for our inputs. Now domain and range, pretty easy. We know domain is going to start at 0 and it's going to go to positive infinity. So we're including 0, excluding infinity. And the same thing happens here with our range, right? If we start at 0 and we go up forever, that means we're going to have 0, comma, positive infinity. We're including 0 and excluding infinity. Okay, so that is our parent graph. That's what it looks like. Let's talk a little bit more about it on this next slide. It says the general equation. Our general equation for a square root function looks like this. Y is equal to a times the square root of x minus h, and then we'll put plus k afterward. So those three parameters that you're used to seeing, a, h, and k, will work the exact same way with this function as it has done with all of the rest. So they're asking us to create equations to transform our parent graph, which, one more time, our parent graph is y is equal to the square root of x. Okay, so we're going to be moving it around based on the characteristics that are given. So the first one, you'll see we want to move it up 5, and we know that that comes from our k. We're going to say y is equal to the square root of x plus 5. The next one is asking us to shift it left 4 and down 2. So I'm going to have y is equal to, now it didn't say anything about a vertical stretch or flipping it. So our a value we would consider to be just 1. And then we're going to take it and we're going to say the square root of x. And remember, if I want to shift it left 4, what we'll see inside of here is plus 4. And then outside we'll say minus 2. And that gets us our function. Now, if you're not sure if you're right or wrong, one thing that you can do is grab out your graphing calculator. And you'll see here, if I go into the y equals, I have the square root of x. And then on this one, I have y equals the square root of the quantity x plus 4 minus 2. When I hit graph, that is what our graphs will look like. Okay, but you'll see that this green one has obviously been shifted to the left 4 and down 2, and that's why that endpoint ends up being down here. All right, now let's jump back into it here. It says we want it to open down and vertically stretch it by a factor of 3. Well, both of these, opening down and then the vertical stretch by a factor of 3, all are affecting a. So I want y equals, and if I want it to open down, I need to have a negative. And then we want it vertically stretched. So that means that our value has to be farther from 0. So we're saying by a factor of 3, that would be like a negative 3. And then we would say times the square root of x. The last one, if we're going to move it to the right 3, just remember we've got y is equal to the square root of x. And if I want to go to the right 3, I'm going to subtract 3. And then we can't shift it up or down, so that would be our answer for that one. Y equals the square root of the quantity x minus 3. And then at the bottom it asks, why does this function have a limited domain? We'll just say we can't take square root of a negative number. All right, the next function is the rational function. Okay, so what rational functions tend to look like is what we call a hyperbola. Okay, so what does it look like? Okay, here's what you need to know about the square root functions. Okay, so we have y is equal to 1 over x as the parent graph. There is a problem though. If I say y is equal to 1 over 0, that doesn't work, right? So we cannot have x be 0. So you also want to think about this. If I said y is equal to 1 over something, and let's say I wanted to take a y and I wanted it to end up equaling 0. There is no value that we can put down here that would cause our output to be 0. So we can't have any inputs that are 0, and we will not have any outputs that are 0. So what does that mean? Well, if I can't put any zeros in for inputs, I'm going to have to draw in a vertical asymptote, okay, where all of our x values are 0. And then we can also put in a horizontal asymptote because we'll never get an output of 0 if we're doing 1 divided by something. So this is what we will end up looking at. All right, so the next thing would be to just come up with some points and graph it on here. So to do that, I've made a couple tables, right? And some of them are kind of easy because remember, you're doing just y is equal to 1 over x. So if we take, like, say on this table here, I plug in -3, I get 1 over -3, or -1/3. This one would be a -1/2. 1 divided by -1 would be -1. 1 divided by -1/2 would be -2. We would end up with a -3, a -4, and then this one is undefined at 0. Let's go ahead and plot those points, see where they are going to be. So we had -3, -1/3, which you'll see is, right down here. And then you have -2, -1/2. And then you've got -1, -1. You have -1/2, -2, -1/3, -3. And you'll see what we're going to get is this shape that runs right along the asymptote, hits these points, and then curls and goes down along this asymptote. Same thing would happen on the other side if we make this table. If I do 1 divided by 1/4, I get +4, which means that 1 divided by 1/3 would be 3. This would be 2. 1 divided by 1 is 1. 1 divided by 2 is a 1/2, and 1 divided by 3 is a 1/3. So you can see here we have some points that are very similar, right? 1/2, 2, and 2, 1/2. We have 3, 1/3, and then 1/3, 3. And that's what helps to create our hyperbola shape. So let's go ahead and plot those points. We have 1/4, 4. We have 1/3, 3. 1/2, 2. We have 1, 1. We have 2, 1/2, and then 3, 1/3. And you'll see it's got that same shape it has down in the third quadrant. So as you're graphing these, the main things I want to make sure that we don't do is cross the asymptotes. And then, your most critical points, you need to know this point, that point, in my opinion. If you know where the asymptotes cross, and you know about that point that's closest to where they cross, it makes life way easier. So our domain here looks like it's going to be from -infinity. I'm going to write it beneath, actually, if I can get a pen that works. So we're going to say -infinity to 0, and then we'll say from 0 to +infinity. I guess you could also write that as x does not equal 0. And then our range is going to actually end up being kind of the same thing, right? So we're going to say -infinity to 0, and then we'll throw the union in there, and then we'll go from 0 to +infinity. All right, so a little bit about our rational functions. Our general equation will be y is equal to, you can either write it as a times 1 over x minus h, and then plus k, or you could write it as y is equal to a divided by x minus h plus k. Okay, so when we just multiply a times that fraction, we know we multiply the a times the numerator. Again, you see your stretch factor, your horizontal shift, and your vertical shift in the problem. They're just going to ask us to rewrite some equations, just like on the last one. Let's get through this one quick. So if we're going to shift it to the right 2, and that's all we're doing, that's going to affect our h. So we know that we're going to have y is equal to x. If I want to go to the right 2, I'm going to put -2. Doesn't say anything about a stretch factor, so we'll leave it as 1 on top. and it has not been shifted up or down, so that is our answer. Let's look at the one beside it. It says vertically stretched with a factor of 2, or I'm sorry, by a factor of 2. So we're just going to say y is equal to 2 over x. Third one. Oh, you had to yawn there. All right, so the third one, we have to move it left 2 and down 3. So we're talking about h and k. So we've got y is equal to 1 over, if I'm moving it left 2, I'm going to say x plus 2. And then we're going down 3, I'm going to put minus 3 down there. Okay, so it's not in the denominator. The minus 3 is like in the numerator. We just don't have a common denominator. And then we want to reflect it into quadrants 2 and 4, because remember, originally it looks like this. It's in quadrant 1 and 3. So to put it into quadrants 2 and 4, we need the opposites. So we're going to say y is equal to a negative 1 over x. And then at the end it says, what is the name of the invisible lines that your hyperbolas will not touch? And that would be asymptotes. And sometimes I spell that wrong. I can't remember if there's 2 S's at the beginning or not, but those are called asymptotes. All right, the last function, y is equal to b to the power of x. However, today we're going to use a value of 2 as our base so that we can get through this a little bit quicker. So this is just an exponential curve. And let's think about what we would have here if we were going to use a table of values. Let's start with the easier part. Let's go down to the very bottom down here. If I said 2 to the third power, that would be 2 times 2 times 2, which is 8. First one I did 2 squared, that's just 4. 2 to the first is just 2. 2 to the power of 0 is 1. And I want you to notice here what's happening as we go from one to the problem to the next, right? We're just cutting everything in half. So when we go from this one into the next one, we're going to have 2 to the negative first, which we know is 1/2. And then we'll go to 2 to the negative second, which we know will end up being 1/4. And then 2 to the negative third, when we plug that in, we're going to end up with 1 over 8. And if you need a calculator to help you with some of those, that's okay, but you know, it's good to try to practice without them. Let's go ahead and plot those on here. So if I'm at negative 3, at negative 1, I'm sorry, positive 1/8, negative 2, I'm at positive 1/4. And those ones are really hard to graph and see, so you can do your best to plot them on there. At negative 1, I'm at 1/2. And now it starts to get easier. We're at 0, 1, 1, 2, 2, 4, and 3, 8. And this is just our exponential curve that goes like this. Okay, you graphed some of those in Algebra 1. Now you're going to graph them in Algebra 2 a little bit. Our domain here is going to be all real numbers. It extends from the left and the right forever. And our range value looks like we're going to go from 0 to positive infinity. However, we're not going to include 0 because it's got an asymptote. And we're not going to include infinity either, just because we usually don't. So our general equation here, y is equal to a times the quantity, actually we'll say times b to the power of x minus h plus k. Now the one that we're doing right now, instead of having b, we have a times 2 to the power of x minus h plus k. So it says create an equation to transform your parent graph for each of the following below. So if you want to shift it down 3, okay, that means that in this case a is going to equal 1, h is still going to be 0, and k is going to end up being negative 3. So we'll say y is equal to a times is 1, so we don't actually have to put the 1. So, but we are going to use our base of 2 in this one. Sorry, I forgot to mention that. So it's like 1 times 2 to the power of x, and then to make it go down, we're going to do minus 3. But you don't have to write this times 1 in there. This doesn't have to be there. To shift it right 4, we know that's going to affect our h, so we'll say y is equal to 2. And if I want to go to the right 4, I'm going to say x minus 4. And then I'm going to say minus 3 afterward. Actually, we weren't shifting that one down. My apologies. Right, we're just shifting that one right 4. I was looking at this one again. And then the last one says vertically stretch it by a factor of 2 and move it up 3. So our stretch factor is 2, so we'll do 2 times 2 to the power of x, and then we would say plus 3. Or a lot of times you'll see it like that with the parentheses.